Welcome to the latest installment in the Physics 150 pre-lectures. In this set of slides, we're going to start integrating the concept of electric potential energy into our discussion, and we're going to introduce a kind of new concept that is given the regrettable name electric potential, but which you perhaps probably better know as voltage. But first, we're going to take a look at electric potential energy. But first, we're going to take a look at gravitational potential energy. If you consider the universal law of gravity as devised by Isaac Newton, you have this expression for force, but there is also an expression for the gravitational potential energy based on that equation. And that equation says that the gravitational potential energy is equal to minus capital G, the gravitational constant of the universe, times the mass of the first object times the mass of the second object divided by their separation. This looks an awful lot like the equation for the force, but the equation for the force, the denominator is s squared. So be very careful about distinguishing between the expression for force and the expression for potential energy, because we're going to see similar confusion when we take a look at the expression for electric potential energy. Let's understand the pieces here, especially that minus sign out front. The minus sign exists in this equation because when I have two masses, they always attract each other. If I have two masses that are close together and they have this gravitational potential energy, if I come along and I do work on each of them and I push them infinitely far apart, and let's say they started motionless, I push them infinitely far apart and they finish motionless, so there's no change in kinetic energy. What happens is they start with some non-zero potential energy, but when they're infinitely far apart, where there's no attraction, there is zero potential energy. So I came along and I added work to the system just to get to zero. I must have started with negative potential energy. So the minus sign exists because these two masses attract each other, and I have to add work to the system just to get them to zero energy in their interaction with each other. The formula for electric potential energy is somewhat parallel to this, that we have a constant, a universal constant, times the property of the first object, times the property of the second object, divided by the separation between the objects. Of course, what these actual values are for electricity is you have K for the constant, the electrostatic constant of the universe, charge of the first object, charge of the second object, but the separation, that's still the same idea. As for the minus sign that seemed to just vanish, this works its way in when you consider if I have two opposite charges, one of these is positive, the other is negative. When I multiply them together, I'm going to get a minus sign, and that would indicate that the potential energy is negative. Well, when I have a positive charge and a negative charge close to each other, they attract each other, and I would have to add energy to the system to get these two objects infinitely far apart. So, two oppositely charged two oppositely signed charges are going to have negative potential energy. On the other hand, if they had similar charges, if they were both positive or if they were both negative, when this is multiplied out and determined on the calculator, you get a positive value for the potential energy. Well, that just means that they want to be pushed away from each other, that this potential energy wants to be converted into kinetic energy. So it's all self-consistent. Negative potential energy means that they attract each other. Positive potential energy means that they repel each other. Let's take a look at this question right here. We have two charges. The separation between them is 4.51 centimeters. They have a total electric potential energy of positive 5.81 millijoules. We're told that both charges are positive, and we're told that one of the charges is twice as much as the other. And the question is, what are those charges? So we don't know what Q1 is, and we don't know what Q2 is, but we are told that one charge is twice as much as the other. So if I set Q1 equal to just Q, that means that Q2 must be equal to 2 times Q. If you follow that, then we can plug into our expression for electric potential energy. We're given that the value of the electric potential energy in standard units is 0.00581 joules, and the separation in standard units is 0.0451 meters. So we have the ability now to algebraically solve for Q. And when we go through it, we get that Q is equal to 1.21 times 10 to the negative 7 coulombs, which is 121 nanocoulombs. A perfectly ordinary value of charge, so there's nothing in there that makes me think that there was some mistake in the math. What if we have more than 2 charges? What if we have 3 or 4 or 5 charges? Well, it's good news, bad news sort of thing. And I'll start with the bad news. And the bad news is, yeah, we are going to be considering these situations. But the good news is when you deal with determining electric potential energy, you don't have to worry about direction. You don't have to worry about treating them as a vector quantity. But the bad news is we have to look at all possible pairs if we want the total electric potential energy of the system. Let's take a look at that. Consider the following situation. We have 3 charges. One is positive 4.51 microcoulombs, the second is negative 3.88 microcoulombs, and the third is negative 813 nanocoulombs. And we're given locations for each of them in respective order. So the 4.51 microcoulomb charge is at 4.1, 2.7, measured in centimeters. The negative 3.88 microcoulomb charge is at x equals negative 1.1 centimeters, y equals 3.5 centimeters. And the negative 813 nanocoulomb charge is at x equals 1.2 centimeters, y equals negative 1.3 centimeters. We want the total electric potential energy of the system. We have 3 charges, and the last bullet point on the previous slide said we need to consider all possible pairs, which means that we have to look at the potential energy between charges 1 and 2, the electric potential energy between charges 1 and 3, and the electric potential energy between charges 2 and 3. In order to do that, we need all of those separations, and so we need to use the distance formula to calculate the separation between charges 1 and 2, the separation between charges 1 and 3, and the separation between charges 2 and 3. And that's what's done in those 3 lines of calculations. A smart person and me would draw a picture. Make sure you distinguish between whether it's a positive charge and a negative charge, and try and put some effort into scaling your picture to represent the actual values given in the problem. So, and here we have 2 negative charges, each is represented by a blue circle. We have a single positive charge represented by a red circle. And in our little sketch, while certainly these charges are not all equidistant from each other, they're all approximately the same distance from each other. So the fact that I got 0.0526, 0.0494, and 0.0532, 3 numbers pretty close to each other, I'm feeling pretty comfortable about those separations. Now we can calculate the total electric potential energy. Like I said, we don't have to touch direction at all, thank goodness. But we do have to add up the separate electric potential energies to get the total potential energy of the system. So we look at KQ1, Q2 over S12 plus KQ1, Q3 over S13 plus KQ2, Q3 over S23. And we can plug in our numbers, and we get negative 3.12 joules. I warned you at the start of the lecture that we would bring up this topic called electric potential, that is better known as voltage. To get a grip of the role of electric potential in electricity, we're going to draw up an analogy yet again with gravity. And that analogy involves topographic maps. On the left-hand side, you see a topographic map of Crater Lake in Oregon. The topographic map shows closed loops that indicate where there's equal altitude. That's what a topographic map does. They show where the altitude is the same. So if you find one of these paths, and if you walk across that path, and you completed that entire loop of path, your height above ground would never change. Your gravitational potential energy would never change. Gravity would do zero work on you if you managed to stay on that path of equal altitude. To understand a little bit better what's going on in electricity, recall the analogy that we had with the electric dipole, in which a positive charge was like a mountain peak and a negative charge was like an undersea valley. On the right-hand side, you see this mountain peak in profile. Imagine you're standing on the ground far away from the mountain. We imagine that the profile is like what you see on the right. But if you could fly overhead in your helicopter, or if you had a topographic map, what you would see are closed loops like on the left. And the smaller the circle is, the higher above sea level you get. We would actually see a very similar thing with an undersea valley, but in the case of the undersea valley, the smaller the circle is, the deeper below water you are. And of course, the undersea valley, instead of an upwards pointing imaginary mountain, we'd have an inverted image, a downward pointing undersea valley. Continuing this analogy, if we have this nice smooth mountain, and if we were to place a rock on the side of that mountain, that rock would start rolling directly away from the top of the mountain. That's represented by the red arrows, indicating placing this rock at different locations. And those arrows, if you'll recall from a previous lecture, represent the direction of the electric field lines. The topographic map is going to represent the voltage. Now, how do I get this justification? Let's go back to gravitational potential energy in a uniform field, like near the surface of the Earth. The formula for gravitational potential energy near the surface of the Earth is mgh. Let's generalize that. M is the relevant property of the object in the field. G represents the field itself, and H represents a location in the field. If I want an electrical equivalent, instead of M, I would have Q. Instead of G, I would have capital E. And as far as location is concerned, I'm just going to use the letter X. And so I could say that the formula for electric potential energy is Q times E times X, but that's not what I'm going to say. Instead, we're going to combine the factors of E and X into a single term. That's done largely because in most situations, the electric field is highly non-uniform. Whereas in a gravitational field that we normally encounter, the gravitational field is highly uniform, and so we can easily separate it out. Whereas in electricity, electric fields can vary widely, even if you travel just a short distance. We take these two complicating factors of field strength and location and combine them into only one complicating factor that we call electric potential. And of course, electric potential, as I said, is probably better known as voltage. If we combine the E and the X in the previous equation into this one quantity, capital V voltage, then our expression for electric potential energy becomes charge times voltage. Not too complicated, at least as far as the equation appears. In many circumstances, we are interested in the voltage difference, and so we could, for instance, look at a revised version of the full-fledged work energy theorem. The work energy theorem could be stated to say that the work done by all non-conservative forces is equal to the change in translational kinetic energy plus the change in rotational kinetic energy plus the change in gravitational potential energy plus the change in elastic potential energy plus the change in electric potential energy. Electricity is a conservative force just as gravity is, so it appears on the right-hand side, if you will, as a potential energy in the equation for the work energy theorem. For what it's worth, we will not ever have a situation in Physics 140 where we deal with all of these concepts simultaneously. That would be ridiculous. And in fact, in Physics 140, you can pretty much count on not worrying about rotational kinetic energy and moment of inertia and stuff like that. In Physics 150, don't worry about moment of inertia, rotational stuff. We could have translational kinetic energy, we could have theoretically gravitational potential energy, we could have electric potential energy. On the other hand, it's unlikely to run into gravitational potential energy because for reasons we've already discussed, pound for pound, the effect of gravity is much less than the effect of electricity. But certainly a change in kinetic energy and a simultaneous change in electric potential energy, that would be fair game. To understand voltage a little bit better, let's compare our expression for electric potential energy with our expression for gravitational potential energy. For electric potential energy, it's Q times capital V. And for gravitational potential energy, we get mgh. Q and M play similar roles. They're the property of the object in the field. And what I'm going to suggest is that you kind of think of voltage as the equivalent of electrical height. How high are you in an electric field or how low you are in an electric field? That's equivalent to asking what is your voltage. And it's just like height and gravity. The greater your height, the more gravitational potential energy you have. There are two commonly occurring voltage situations. One is when we have a uniform electric field, and the other is when we are dealing with point charges. If we have a uniform electric field, we can calculate the voltage difference as minus the field strength times the difference in displacement. We only worry about the component of displacement that's parallel to the electric field. If we have point charges, we have an expression that allows us to determine the electric potential or voltage of a single charge, and it's equal to K times Q over S, where S, of course, is how far away your point of interest is from the charge itself. Let's take a look at some examples. Let's suppose we have a uniform electric field, and it's equal to negative 1,710 newtons per coulomb. Then you see this I hat, and I hat is an engineer's notation for saying X hat, or along the X direction. So in other words, this uniform electric field is parallel to the X-axis, and it points in the minus X direction. The question being asked is how much work is there in moving a motionless 17.5 microcoulomb charge from one location to another location, and assume that afterwards it's subsequently motionless. Let's make sure we understand this. We have a uniform electric field, so if we go back to the previous slide, we're going to want to use the formula delta V equals minus E delta X. Well, we have E, that's given, and we have enough information to determine delta X. Delta X is final minus initial. The final value of X is 1.55. The initial value is 8.11. Now, I only worry about the difference in X. I do not worry about the difference in Y, because the electric field is only parallel to the X-axis. If the electric field had any component along Y, then yes, I would have to worry about it, but that's not the case here. We can now calculate the change in voltage. It's minus the electric field times the change in displacement. The electric field is negative 1,710, and the change in displacement, at least the X component, is negative 6.56 meters. So we have negative 1,710 times negative 6.56, and we wind up getting a potential difference, a voltage difference, of negative 11,217.6 volts. Sounds like a lot, and goodness knows I would hate to be caught in that sort of situation, a high voltage situation, but this is not an outrageous value for the voltage. High voltage power lines, for instance, will have voltages that are tens of thousands of volts or even hundreds of thousands of volts. Later this semester, we'll see why those voltage lines had such large voltages. The work is equal to minus the change in the potential energy. That business still holds true from way back when. And so minus the change in potential energy, we get minus Q times delta V. So minus 17.5 times 10 to the negative 6 times minus 11,217.6. And we wind up with a work of 0.196 joules, which sounds a lot less intimidating than 11,217.6 volts. So perfectly ordinary value for the work done. Keep in mind that there should be some consistency between the answer you calculate and your expectations. We have a charge that is moving in the negative X direction. The electric field is in the negative X direction. Let's think about this a little bit in terms of gravity. The gravitational field points down. It points in the direction of decreasing height. And if I place a mass in a gravitational field and that mass falls, the gravitational field is going to do positive work on it. It's going to work at attempting to speed it up. Well, that's kind of what's happening here. We have a positive charge in an electric field. The electric field is pointing to the left. The positive charge moves to the left. So this positive charge is moving in the same direction as the electric field, just as a falling mass is moving in the direction of the gravitational field. Positive work will be done by the field on the object. Bear in mind, unlike gravity, we have both positive and negative values for the charge, and so a positive charge moving in an electric field, the electric field will try to push the positive charge down voltage the same way that a gravitational field tries to push a mass downhill. On the other hand, in electricity, if I have a negative charge in the electric field, the electric field wants to push the negative charge up voltage. It wants to push it in the direction of higher and higher voltage, spontaneously. As I said, the other situation in which we will be looking at voltage is that for point charges. And electric potential has the same advantage as electric potential energy, and that direction is not important. So take a look at the example. Negative 991 nanocoulombs, positive 1.27 microcoulombs, positive 2.35 microcoulombs, and we have those respective points measured in meters. So negative 991 nanocoulombs is at negative 1.7 meters, negative 3.1 meters. Positive 1.27 microcoulomb charge is at negative 2.5 meters, 1.7 meters. And the positive 2.35 microcoulomb charge is at 4.1 meters, negative 2.2 meters. And the question is, what is the electric potential at the point x equals 3 meters, y equals 3 meters? That's our point of interest. We have to start by determining the separation from the point of interest to each charge. So how far away is 3, 3 from charge 1? How far away is 3, 3 from charge 2? How far away is 3, 3 from charge 3? And you can see the values calculated on the screen. S1 equals 7.70 meters, S2 equals 5.65 meters, S3 equals 5.32 meters. So now we know the S's, we're given the Q's, we can solve for the electric potential. The electric potential is equal to K times Q1 over S1 plus K times Q2 over S2 plus K times Q3 over S3, and we calculate the electric potential at this point to be 4,835 volts. Again, a perfectly ordinary value for voltage. Even if it sounds high for everyday life, it's actually pretty ordinary in electricity in general. I also want to bring up the idea of electric potential in the situation of the electric dipole. And you can see on the screen that we have an electric dipole, equal but opposite charges in close proximity to each other. And the curves that you see on the screen are like a topographic map. They represent locations of equal voltage. If the red spot represents the top of the mountain peak and the blue spot represents the bottom of the undersea valley, then each curve that you see, each closed loop that you see, represents a path along which the voltage does not change. You will see exactly midway between them a vertical line. That vertical line is like sea level. Sea level, of course, is at a height of 0, and in this electric dipole, this vertical line is at a voltage of 0 volts. The closed loops to the right of the vertical line are at negative voltage, just as a height could be at a depth below sea level, and the closed loops to the left of the vertical line are above sea level, so they do represent a height as you know and understand it. Okay, that's all for now, and we'll do this again. Take care.